All right, welcome everybody. In this video, we're going to give a quick little dive into normal distributions, and we'll delve much deeper into normal distributions and other continuous random variables in class together. And we use normal distributions in situations where data tends to be distributed symmetrically about a central value with no bias towards the left or towards the right. And so, for example, in this image, we're looking at a bunch of students that are lined up by height. The shortest students on the left, the tallest students on the right. And this curve is indicating that the distribution of heights follows this trend where most of the students are lined up in the middle, average heights. And as we move away from the middle, as we move to the right, students are getting taller, but it gets less and less frequent that we see really, really tall students. And as we move to the left, students are shorter than average. And the further from the mean we get, the less frequent we observe those values. And so normal distributions, they occur in many situations, such as heights of people, size of items being produced. And for us this semester, most importantly, they come up in statistics when we are repeatedly picking from a population independently each time. And normal distributions have two parameters. One of them is the mean that gives us the center of the distribution, and the mean we typically denote with the Greek letter mu. The second parameter that we need to describe a normal distribution is not just where is it centered, but how spread out are the values under this distribution. And that's what we call, as we've seen, the standard deviation. And we denote that with a sigma when we're dealing with a population of data. So if a random variable x is normally distributed with mean, mu, and standard deviation, sigma, then we write x is distributed with a normal distribution. We denote this with an n. And our two parameters are the mean, mu, and the standard deviation, sigma. And so if we take a look below, we can see here is a plot of two normal distributions. Note these two distributions are both symmetric and bell-shaped. The distribution in red, this is what we call the standard normal distribution. Its mean is 0 and its standard deviation is 1. The distribution that is sketched in blue, this is a normal distribution that also has the same mean, 0, so these are centered at the same point, but the standard deviation is bigger. This blue graph has a standard deviation of 2, and so we can see that makes the values more spread out, and as a result, this distribution gets flatter, gets shorter, and fatter, gets wider. So the peak in the middle gets pushed down, and we have more values on the edges. And if we change the mean around, that's going to be the equivalent of shifting the normal distribution. So in red, we have the standard normal distribution with mean 0 and standard deviation 1. And the graph in blue is the normal distribution with mean 3 and the same standard deviation 1. So the shape hasn't changed. We just shift this red graph 3 units to the right, and its center is now located at mu is equal to 3. Normal distributions are continuous random variables. And so as we've seen with other continuous random variables, if I want to calculate the probability that random variable x is between a and b, then we need to go ahead and take a look at the PDF of the random variable, and we'd like to calculate the area under the corresponding PDF between A and B. So in other words, in order to work with probabilities for continuous random variables, we need to be able to calculate areas beneath the PDF of the random variable. And we've seen some examples where we were able to use geometry to calculate areas of rectangles and triangles. In some cases, we've worked with integrals. We'll have to learn some additional tricks to work with normal distributions. And one such nice trick to get approximate values is to use what's called the empirical rule. So the empirical rule tells us that if we start at the mean, which is indicated at 0, for any distribution which is normally distributed, if we go one standard deviation above the mean and one standard deviation below the mean, then in the middle, inside this region, we have an area which is accounts for 68% of the total area. And if we were to move one more standard deviation out, and we were to go 2 standard deviations above and below the mean, then inside this region, we have 95% of the data. And going one more standard deviation away from the center, we can see here we've got going from +3 to -3, we've got 99.7% of the data. So nearly all of the data is within 3 standard deviations of the mean. And so this is often called the empirical rule. This is a nice approximation that we can apply to normal distributions. This same rule doesn't apply to distributions in general. This is just a good rule of thumb that we can use when working with normal distributions. And as we've seen, one place where normal distributions have come up is looking at distributions of heights. Another metric that is often normally distributed is what is called the body mass index, or BMI. And this is a metric which uses both the weight and the height of an individual to calculate what is called the body mass index. And the background for the example that we're going to get into on the next slide is that a number of years back, about 10 years ago, Israel was concerned about body image issues, and in particular with models that were advertising certain products. And they didn't want to have what they deemed underweight models that would give bad body image issues. So they needed to set a metric for what would be a healthy weight for that models would need to satisfy. And they came up with a body mass index of 18.5. So if you were an aspiring model and you have a body mass index less than 18.5, you were unable to get employed as a model. So in the next couple of examples, we'll take a look at just how extreme is a body mass index of 18.5. Okay, so now let's take a look at just the adult men in Israel. So we'll denote the BMI of a randomly selected adult male in Israel as X. And what we know from data is that the distribution of BMI of adult males in Israel is approximately normally distributed with a mean of 26 and a standard deviation of 4 BMI units. So on the right, I've sketched out a rough sketch of this normal distribution. And so notice I want to use the empirical rule. So it's going to be useful to know exactly what would one standard deviation above the mean be. So I've marked the mean at 26. Every time we go up by 1 standard deviation, that's the equivalent of going up by 4 BMI points. So here's 1 standard deviation above at 30. The next standard deviation would put me at 34 and 38. And similarly, going 1 standard deviation below the mean would mean we go 4 BMI units below, and that would put us at 22 and then 18 and then 14 over here. And so if we want to calculate what proportion of adult men in Israel have a BMI between 26 and 30, well, then we can indicate that area on this graph over here that I'm shading in red. And notice that this area is 1/2 of the 68%. So if we were to go 1 standard deviation above and below the mean, that would account for 68% of the data. And here we've got half of that. And since the normal distribution is symmetric, then we're going to take this 68%, divide that by 2, and that gives us 34%. So for the first question here, we could say that the proportion of men in Israel that have a BMI between 26 and 30 is approximately 0.34, or about 34% of the men. And for the women in Israel, the BMI is distributed pretty closely, but not exactly the same. So if we let Y denote the BMI of a randomly selected adult women in Israel, these BMIs are approximately normally distributed with a mean of 26.5, so a little bit bigger than the distribution of males. The standard deviation is 4.5, so it's going to be a little bit more spread out than the males, but roughly the same. And I've drawn this distribution on the right as well. And so here the mean is at 26.5, and every time we go up a standard deviation, we go up now by 4.5 BMI units. And every time we go down by one tick, one standard deviation, we're going down by 4.5 BMI units. And let's similarly look at a probability question that is going to ask us for the distribution of what proportion of women in Israel have a BMI between 22 and 35.5. So let's sketch this on the graph below. So here we are at 22, and here we are at 35.5. And the proportion of women that have a BMI between 22 and 35.5, I've shaded in blue. And so there are many different ways that you can imagine chopping this area up into different pieces and calculating the area of those pieces. So I'm just going to go through one possible way, but you may be thinking about this in a different way and get the same exact answer. So building off of what we talked about before, over here between 22 and 26.5, this is 1/2 of the 68%. So recall 68% of the data is within plus or minus one standard deviation of the mean. So if I go just one standard deviation below, we're going to get half of that 68%. And then we can similarly calculate the area on the other side that goes from 26.5 to 35.5 by saying with two standard deviations above and below the mean, that should account for 95% of the data, and that would go from here to here, but we only have half of that. So we would take this 95% divided by 2, and that gives us 47.5%. And so we take this 47.5, we add it to the 34%, and that gives us 34% plus 47.5%, which gives us 81.5%. So the proportion would be approximately 0.815, and that represents, again, the proportion of adult women in Israel that have a BMI between 22 and 35.5. So as we've seen, the empirical rule gives us pretty nice approximations when we're working with values of x that are really close to being 1 or 2 or 3 standard deviations from the mean. But let's say we want to answer a question like, what proportion of adult men in Israel, X, have a BMI which is less than 21? Well, the empirical rule can give me a rough idea. I can see, well, 21 is not quite 2 standard deviations below the mean, but it's a little bit more than 1 standard deviation below the mean. So it's somewhere between 18 and 22. So it's somewhere between 1 and 2 standard deviations below the mean. So we can ask more precisely, well, how many standard deviations is x equals 21 from the mean, which was 26? And that is exactly what the z-score measures. So the z-score, the formula is given over here. We calculate by taking x minus mu, and so that is essentially calculating the distance of the value from the mean in terms of units of x. So that would be telling me that 21 is 5 units of BMI below the mean. And then we scale that distance relative to the standard deviation. So then we would say this distance of 5 BMI units from the mean, well, how many standard deviations is that? So let's take a look at what that calculation would look like if we wanted to calculate the z-score for a male that has a BMI of 21. We would take that 21 minus 26 to give us minus 5. And again, that's this absolute distance. And then we scale that by 4 because the standard deviation for men was 4. and we can see that the z-score comes out to minus 1.25. So this minus 1.25 I've marked over here. So X value of 21 has a z-score of minus 1.25, and that is telling me that a person with a BMI of 21 is 1.25 standard deviations below the mean BMI. And this process of standardizing or normal distribution, so taking all of these values of X, and rather than describe X in terms of BMI units, we describe X in terms of its z-score, in terms of how far away from the mean is what's called standardizing or normal distribution. So the standard normal distribution, that is what is pictured on the right, and that is the distribution whose mean is 0 and standard deviation is 1. And standardizing was particularly useful back in the days when we used tables to calculate areas beneath normal distributions. So this probability that X is less than 21 is going to equal the same exact area as the probability that we have a BMI that has a z-score which is less than 1.25. And so we can see that the area, again, corresponding to the proportion of men that have a BMI less than 21 is equal to the area to the left of the z-score minus 1.25 under the standard normal distribution. But we're going to calculate these probabilities more precisely using R in a moment. So let's take a look at another example of z-scores, and let's consider this BMI example where in Israel they passed this law that said if you have a BMI less than 18.5 that you are unable to legally be hired as a model. And so if we're considering the women in Israel that have a BMI which is normally distributed with a mean of 26.5 and a standard deviation of 4.5, well, just how extreme is a BMI of 18.5? So let's calculate the z-score for an Israeli woman that has a BMI of 18.5. Then we'll interpret the meaning of that value. So recall that to find the z-score, we take our value X, in this case 18.5, and we subtract the mean from it, the 26.5. Then we divide that difference, which is telling me how far this value is in terms of BMI, by the standard deviation. So we're going to rescale that difference to describe it in terms of how many standard deviations is that distance. So in this case, we divide it by the standard deviation of 4.5, and we get a z-score of approximately minus 1.778. And what that means in practical terms is that an adult woman in Israel that has a BMI of 18.5, well, that is 1.778 standard deviations below the mean BMI for women, which was 26.5. Okay, so let's say we want to calculate what proportion of all individuals, in this case, X is going to denote a randomly selected adult woman in Israel, what proportion of that population has a BMI which is less than 18.5. So the empirical rule is not going to work perfectly here because it's going to give us a rough approximation because this is not a nice round number from the mean. So instead, maybe we can think about using integrals. We've used integrals before to calculate these areas. And so if I know a formula for the PDF, so up top is this normal distribution, it's a curve. And we can model that curve. It has a formula which is given below. And notice this formula is super cool. It has everybody's favorite irrational numbers in it, namely pi and e. Okay, so this is a pretty crazy looking formula, but it actually gives us this curve up top. So if I want to calculate what proportion of the population has a BMI less than 18.5, well, why not just set up an integral in this case? So now we're going to integrate, let's say the smallest BMI is 0 up to our value 18.5. And now I've got this formula. I can plug in 4.5 for sigma, and I can plug in 26.5, the mean for the women, in place of mu. And why not just evaluate this integral? Well, good luck with that one. You cannot actually evaluate this definite integral using antiderivatives. So instead, you would need to use some approximation methods like using Riemann sums. But on the last slide, I want to show you how we can calculate these probabilities with built-in functions in R. Okay, and so finally, let's show how we can work with normal distributions in R. And so let's use our motivating example of we are working with a normal distribution of BMI X for women, which is normally distributed with a mean of 26.5 and a standard deviation of 4.5. And we want to calculate what proportion of this population has a BMI less than 18.5, would not be able to be hired as a model legally. And so we can represent that area below under this normal distribution over here. And we've talked about how we can use z-scores and empirical rule to get approximations for that area. R has a nice built-in function for the normal distribution. We put a p before it, as we've seen before, to calculate the probability that x, capital X, is going to be less than this value x that we enter first into this function. Next, we enter the mean, and then finally the standard deviation. So it takes three values in the function, and what comes out is going to be the area to the left of that value x. And here I've copied and pasted what the code would look like in R, where notice I plugged the 18.5 in first, followed by 26.5 for the mean, and lastly the standard deviation of 4.5, in outcome 0.0377 to so on. This value over here corresponds to this little sliver of area over here, and that tells me that about 3.77% of adult women in Israel have a BMI that's less than 18.5. So that's a pretty extreme BMI to have. You could have also used the standard normal distribution to calculate this. Recall that 18.5 had a z-score of minus 1.778, and I've kind of truncated this decimal. The 7 is repeating. And with a standard normal distribution, we have a mean of 0 and a standard deviation of 1. And down below, we get a very almost identical value. The only reason why there's a difference in these two values is because I rounded off the z-score, which has a repeating decimal. And the default in R is that the mean and the standard deviation are 0 and 1. So if you leave off the mean and the standard deviation, it's going to assume that you are meant to enter a z-score with the standard normal distribution. And so we'll dig deeper into normal distributions in class, but just to end things in this video, I want to introduce just a couple of other functions that are built into R that work with normal distributions. One is the Q-norm function, and we're going to use this to find quantiles of normal distributions. Another is R-norm, which we use to randomly select values from a normal distribution. And in the past, with discrete normal distributions, we've seen that there's functions d, enter the distribution name, that can be useful. With continuous random variables, we're not going to want to use this d function. So we're not going to want to use d-norm to calculate any probabilities.